All right. Good day, everyone, especially to Engineer Tobola. I am Diana Miranda, and along with me are Leonard BANIQUED, John Loyd, LEDESMA, and Nathaniel NATIVIDAD. We will be discussing energy and environment, particularly focusing on air pollution. Um, Let me start by saying that everything we do in our lives, even as we breathe, causes conversion of energy from one form to another. We enjoy electricity, transportation, food production, and different leisures in the expense of damaging our environment. Our modern lives are powered by burning of fossil fuels such as coal, oil, and natural gas since the 1700s. Considerable amounts of pollutants are emitted as the chemical energy in fossil fuels is converted to thermal, chemical, or electrical energy, all via combustion. And thus, we might associate pollution to power plants, industrial processes, motor vehicles, residential and commercial energy consumption, and even small things like stove. The largest sources of air pollution are the industrial activities and motor vehicles. And the pollutants released by them are usually grouped as hydrocarbons, sulfur dioxide, nitrogen oxides, particulate matter, and carbon monoxide. Pollutants emitted during the combustion of fossil fuels contribute to smog, acid rain, and climate change. And these phenomena have direct effects on vegetation, wildlife, and human health. Concerning human health, children are the most susceptible to the damages caused by air pollutants, and they are also more exposed to pollution as they are more active and they breathe faster. On the other hand, people with heart and lung problems are most affected by air pollutants. This becomes apparent when the air pollution levels in their neighborhoods rise to high levels. It is estimated that over 60,000 people in the United States alone die each year due to heart and lung diseases related to air pollution. Locally, here in the Philippines, in 2018, WHO reported that there were 45.3 air pollution related deaths for every 100,000 people in the Philippines. This was the third highest in the world after China and Mongolia. Now, what are the actions done by the states? In the United States, they have the Clean Air Act of 1970, which set limits on pollutants emitted by large plants and vehicles. And as a result, their pollutants have been declining steadily since 1970s. Locally here in the Philippines, we have the Philippine Clean Air Act of 1999 or the Republic Act number 8749, which provides for the creation of a national program of air pollution management, focusing primarily on pollution prevention for the promotion of mass media communication in order to create social awareness and active participation in air quality planning and monitoring. Um, Moving on, we will be discussing different pollutants that can be found in the environment. Here, the diagram shows a basic representation of how fossil fuels, such as coal, oil, and natural gas, are processed. Fossil fuels are burned with oxygen gas and nitrogen gas in the chamber of combustion or the combustion chamber. Normally, it would produce carbon dioxide, hydrogen oxide, nitrogen gas, and oxygen gas, which are not so very toxic. However, due to circumstances to be discussed, um, the combustion produces air pollutants. Um, Hydrocarbons, carbon particles, um, and um, carbon monoxide emissions are mainly produced due to incomplete combustion, which may be due to insufficient oxygen, insufficient mixing of fuel and air, etc. However, sulfur dioxide is inevitably produced when the fuel contains sulfur. Sulfur is a fuel which reacts with oxygen to form sulfur dioxide. Nitrogen oxide generation is due to high temperature reactions between atomic nitrogen and oxygen. Particulate matter is commonly called ash, and it is produced mostly when coal or oil is burned. A combustion process is complete if all the carbon in the fuel burns to carbon dioxide, and all the hydrogen burns to H2O, and all the sulfur, if there is any, burns to sulfur dioxide. Conversely, the combustion process is incomplete if the combustion products contain any unburned fuel or components such as carbon particles, hydrogen, carbon monoxide, or other mentioned earlier pollutants. It occurs when there is insufficient oxygen, or if there is more oxygen is present in the combustion chamber than needed for complete combustion. It also occurs when there is insufficient mixing in the combustion chamber during the limited time that the fuel and the oxygen are in contact, and dissociation, which becomes important at high combustion temperatures. The first pollutant to be discussed is the particulate matter. Particulate matter may be defined as small solid and liquid particles suspended in the air. It could be dust particles from roads and construction and agricultural activities. Could be iron, silicon, soil, and materials of earth, and nitrates and sulfates formed as a result of sulfur dioxide and nitrogen oxide emissions. When the particles are less than 10 micrometers, they are called PM10 and classified as coarse. PM2.5 refers to particles less than 2.5 micrometers and referred to as fine. Particulate matter are associated with significant health effects in the particular respiratory diseases such as asthma and bronchitis, cardiovascular and lung diseases, lung tissue damage, visibility impairment, and even cancer. PM2.5 can penetrate deeply into the respiratory system, and therefore it is more dangerous to health than PM10. The combustion of coal produces large amounts of ash, which should be removed in a safe and effective manner. In coal-fired power plants, ash particles are carefully collected from the combustion gases. However, some ash and other particulates still remain in the combustion gases and emitted to the atmosphere. It is estimated that about 1 gram of particulate matter is released to the environment for each kilowatt hour of electricity produced from a coal-fired power plant. The collection of ash from coal-fired plants involves some water pollution, as water is used to transport ash in the plant. These ash particles are released to the environment when this water, along with other water streams, is discharged to the lakes or rivers. In a coal-fired power plant, the flying ash particles, or flash, in combustion gases can be removed and safely collected by various means. One common way is by using a device called an electrostatic precipitator. Electrostatic precipitator prevents flying ash particles from being emitted to the atmosphere. An ESP is very effective as it removes more than 99% of the ash in the combustion gases. Next, now we can proceed in sample problems. Consider a coal with the following composition on a mass basis: 67% carbon, 5% hydrogen gas, 9% oxygen gas, 2% nitrogen gas, 1.5% sulfur, and 8.5% ash, and 7% moisture. The heating value of the coal is 28,400 kilojoules per kilograms. This coal is consumed in a power plant at a rate of 2,000 kilograms per day. The plant operates 65% of the time annually. For letter A, determine the amount of ash entering the plant per year. The plant operates 65% of the time. Then the total number of operating days in a year is 237 days per year. The total amount of consumption in a year is 474,000 kilograms per year. It was obtained by multiplying the operating days and the given consumption rate. Noting that 8.5% of coal is ash, the amount of ash entering the plant per year is therefore 40,290 kilograms per year. For letter B, we are to determine the amount of ash entering the plant per megajoules of heat input to the plant. The total heat input to the plant in a year is obtained by multiplying the consumption rate, the given consumption rate, the operating days, and the heating value of the coal, which will give us 1.346 times 10 raised to 10 kilojoules per year. The amount of ash entering the plant per megajoules of heat input to the plant is then 0.00299 kilograms per megajoules. Next air pollutant in the list is the sulfur dioxide. Fossil fuels are mixtures of various chemicals, including some amounts of sulfur. The sulfur in the fuel reacts with oxygen to form sulfur dioxide, which is an air pollutant. Coal contains the most amount of sulfur among fossil fuels. Low sulfur is more desirable, of course, but has higher monetary value. The main source of sulfur dioxide is the electric power plants that burn high sulfur coals. Also, volcanic eruptions and hot springs are also releasing sulfur oxides, which causes the rotten egg smell. When a coal is burned, more than 95% of sulfur is oxidized to sulfur dioxide. About 2 to 5% of sulfur in the coal does not get burned and ends up in the solid ash particles. Also, motor vehicles also contribute to SO2 emissions, since some motor vehicles use diesel fuel, and diesel fuel also contains small amounts of sulfur. However, recent regulations have reduced the amount of sulfur in diesel fuel. SO2 emitted from the combustion and other systems can react in the atmosphere to form sulfates, which are components of acid rain, as shown in the figure in your lower left corner. Sulfur dioxide is a very toxic pollutant with very serious health effects, as shown in the figures. It requires a shorter exposure time at higher SO2 concentrations for significant health impact. However, longer exposures at low concentrations and shorter exposures at high concentrations may result in the similar health effects. When SO2 level in atmosphere is more than 1 part per million, it can lead to airway constriction. The health effects of SO2 includes respiratory, lung, and cardiovascular illnesses. Children and elderly, again, with asthma and breathing problems are more sensitive to sulfur dioxide exposure. Now, we again proceed to sample problem. A coal-fired power plant generates 300 megawatt power with an overall efficiency of 35%. The capacity factor of the plant is 70%. The coal used in the plant has the following composition on a mass basis: 67% carbon, 5% hydrogen gas, 9% oxygen gas, 2% nitrogen gas, 1.5% sulfur, and 8.5% ash, and 7% moisture. The heating value of the coal is again 28,400 kilojoules per kilogram. For letter A, determine the amount of sulfur entering the plant per year. The capacity factor of the plant is given to be 70%. That is, the plant operates 70% of the time. Then the annual operating hours are therefore 6,132 hours per year. For the rate of heat input, it can be obtained using the plant efficiency equation, and a little manipulation will get us rate of heat input equals power over plant efficiency, which will give us 857.1 megawatts. The amount of heat input in the plant per year is will be obtained by multiplying the operating hours and the rate of heat input, which will give us 1.892 times 10 raised to 13 kilojoules per year. The corresponding coal consumption by the plant per year will be 6.662 times 10 raised to 8 kilograms per year. The mass percentage of sulfur in coal is given to be 1.5%. Using that, getting the 1.5% of 6.662 times 10 raised to 8 kilogram per year, we get 1.999 times 10 raised to 6 kilograms per year. For letter B, determine the amount of sulfur dioxide produced after the combustion process if all sulfur reacts with oxygen gas during combustion. Note that sulfur dioxide is produced according to the reaction oxygen gas added to sulfur yields to sulfur dioxide. That is, for 1 kilomole of sulfur entering the reaction, 1 kilomole of sulfur dioxide is produced. The molar masses are 32 kilograms per kilomole for sulfur, 32 kilograms per kilomole for oxygen gas, and 64 kilograms per kilomole for sulfur dioxide. Therefore, for 32 kilograms sulfur entering the combustion process, 64 kilograms of sulfur dioxide is produced. All this will give us 1.999 times 10 raised to 7 kilograms per year. Next.
Okay. Next on our list is nitrogen oxide. Nitrogen oxide and nitrogen dioxide are produced during the combustion of fossil fuels such as coal, oil, and natural gas. It is formed when nitric oxide and nitrogen dioxide is combined. The ones that are responsible for these things are electrical power plants, automobiles, and other vehicles burning fossil fuels. Most of the nitrogen oxide emissions from combustion system to the atmosphere are nitric oxide, but it gradually turns into nitrogen dioxide by reacting with oxygen air. Nitrogen oxides are produced at high combustion temperatures when a fuel is burned with oxygen in air. A number of possible reactions can contribute to the formation of nitric oxide and nitrogen dioxide, and some of these reactions are as follows. As we can see here, monoatomic oxygen reacts with N2, and that will result to NO. Another one is monoatomic nitrogen reacts with O2, and that will form to NO, and so on. And at higher combustion temperatures, more dissociation reaction cause greater amounts of nitrogen oxide production, and very little nitrogen oxide is formed at low temperature. Nitrogen is normally stable in air as diatomic or N2 and does not react with oxygen. However, some nitrogen breaks down at high combustion temperature as a result of dissociation reaction. And also here, at high combustion temperature, O2 and H2O also dissociates as follows. Nitrogen oxide emissions are greatly reduced in gasoline automobiles by the use of catalytic converters, and this will be further discussed later on. In diesel engines, catalytic converter is not much effective in reducing nitrogen oxide. Instead, they use exhaust gas recycling. It is used effectively to control nitrogen oxide generation. In AGR, some exhaust gases up to 30% are diverted back to the combustion chamber. Let's take this example to compute for the nitrogen oxide emissions in a natural gas power plant. The problem is the maximum allowable nitrogen oxide emissions for fossil fuel power plants built after 1997 in the United States is specified to be 0.72 grams per kilowatt hour or 65 nanograms per joule of fuel heat input to the boiler. A natural gas-fired power plant consumes 15 kilogram per second natural gas and produces 375 milliwatts of power. It is estimated that nitrogen oxide emissions from this power plant is 65 nanogram per joule. The heating value of natural gas is 55,000 kilojoules per kilogram. The first thing that we need to determine is the overall plant efficiency. The next is the equivalent nitrogen oxide emissions in terms of grams per kilowatt hour of electricity produced. And the last one is if the plant operates 8,000 hours in a year, determine the amount of nitrogen oxide emissions per year. Now, in order to get the overall plant efficiency, we need to determine first the rate of heat input of the plant. And that is, we can get that by using this formula. Q is equal to mass of the natural gas times the heating value. And that will give us 825 kilowatts. And to get the efficiency of the plant, we need to divide the power generated and the rate of heat, which will give us 45.4%. The letter B. The plant efficiency shows that 1 joule of heat input to the plant, 0.4545 joule of electricity is generated. Then the specified nitrogen oxide emissions can be expressed in grams per kilowatt hour unit as we just need to convert the joule to kilowatt hour, and using this conversion, that will give us 0.515 grams per kilowatt hour. The last one, the amount of heat input for an annual operating hours of 8,000 hours is, we just need to multiply the rate of heat that we solved earlier, and we need to multiply it by the operating hours, which is the 8,000. And that will give us 2.376 times 10 to the 13th power kilojoule per year. Noting that the nitrogen oxide emissions from this power plant is 65 nanogram per joule of heat input, the amount of nitrogen oxide emissions per year is determined as this, and multiply it with the 65 nanograms per joule in order to cancel out the joule and for the kilogram to remain. That will give us 1.544 times 10 to the 6th kilogram per year. Therefore, this natural gas-fired power plant is responsible for 1,544 tons of nitrogen oxide emissions to the environment a year. Next one is the hydrocarbons. Fossil fuels, coal, oil, natural gas are primarily made of hydrocarbons. In a combustion reaction, some of the fuel cannot find oxygen to react with during the combustion period. As a result, some unburned or partially burned fuel particles leave the exhaust gases as HC components. And insufficient mixing between fuel and air, non-homogeneous mixture, and short time of reaction are some of the causes of incomplete combustion and resulting HC emission. And the terms hydrocarbons or HC and volatile organic compounds or VOC are usually used interchangeably. However, some of VOCs found in an automobile exhaust also contains component other than HC such as aldehydes. A significant portion of VOC or HC emissions in vehicles are caused by the evaporation of fuel during refueling or spillage during spitback or by evaporation from gas tanks with faulty caps that do not close tightly. The solvents and propellants and household cleaning products that contains benzene, butane, and other HC products are also significant sources of HC emissions. Additional sources of HC emissions include venting of crankcase, petroleum refineries, chemical plants, and etc. When diesel fuel is burned in an internal combustion engine, combustion gases contain unburned carbon soot particles, which are sometimes seen as black smog. Carbon soot particles are usually in the form of spears with diameter between 10 and 80 nanometers. The carbon particles or the particles are essentially solid carbon with some HC on the surface. And these soot particles may find oxygen to react with by the time the combustion is finished, and that will yield carbon dioxide. The next one is the carbon monoxide. Carbon monoxide is a colorless, odorless, poisonous gas. It is mostly emitted by the industry and motor vehicles, and it can build to dangerous levels in areas with heavy congested traffic. CO is produced during combustion when there is fuel-rich mixture, not enough air or oxygen in the fuel mixture. During the combustion of an HC fuel, carbon reacts with oxygen according to the reaction, as we can see here, that will yield to carbon monoxide. And the resulting carbon monoxide is also a fuel with energy content heating value of 10,100 kilojoule per kilogram. It further reacts with oxygen again to form carbon dioxide to complete the reaction, as you can see here. Now, CO2 is produced at engine startup and acceleration, during which the engine runs with fuel-rich mixture. The percentage of CO2 in the exhaust of a gasoline engine can be as low as 0.1% and as high as 5%. Carbon monoxide deprives the body's organs from getting enough oxygen by binding with the red blood cells that would otherwise carry oxygen. So as you can see here, it is actually bad for our health. Now, to further solidify that statement, we have here this figure, the effect of carboxy hemoglobin, or the CO absorbed in hemoglobin, on the human body. Now, negative physiological effects on the body are observed when the levels of carboxy hemoglobin is above 100 parts per million. Here, parts per million, or 0.01%. Serious effects including coma takes place after 300 parts per meter, and long-term exposure above 600 parts per million is fatal. And the last one is ozone, smog, and acid rain. Smog is smoke plus fog, and it is also called photochemical smog, and is made up mostly of ground level ozone, or O3, but it also contains numerous other chemicals including carbon monoxide, PM such as soot and dust, volatile organic compounds such as benzene, butane, and other HCs. The harmful ground-level ozone should not be confused with the useful ozone layer high in the stratosphere that protects the Earth from the sun's harmful ultraviolet rays. Ozone at ground level is a pollutant with several adverse health effects. It is harmful to the lungs, other biological tissue, and trees. It can react with rubber, plastics, and other materials with serious damage. Agricultural crop loss due to ozone in the United States are estimated to be more than $500 million per year. The primary sources of nitrogen oxides and hydrocarbons are motor vehicles and power plants. Hydrocarbons and nitrogen oxides react with the presence of sunlight on hot, calm days to form ground-level ozone, which is the primary component of smog, as you can see here. The smog formation usually peaks in late afternoons when temperatures are highest and there is plenty of sunlight. Ozone irritates eyes and damages the air sacs in the lungs, where oxygen and carbon dioxide are exchanged, causing eventually hardening of this soft spongy tissue. It also causes shortness of breath, fatigue, headache, and many more. The most effective method of reducing ground level ozone involves minimizing nitrogen oxide and HC emissions. Now let's go to acid rain. The sulfur oxide and nitric oxide reacts with water vapor and other chemicals high in the atmosphere in the presence of sunlight to form sulfuric acid and nitric acid. Sulfuric acid forms when sulfur dioxide reacts with water and dissolved oxygen. That will yield H2SO4. Another is reaction of SO2 produces sulfurous acid. And both sulfuric acid and sulfurous acid are components of acid rain. Acid droplets can penetrate deeply into lungs during respiration. When SO2 produced from power plants are transported through long distances due to winds, it may be transformed into sulfate particles and other acidic species. Also, NOx emissions cause the formation of nitrate species, sulfates, nitrates, and other acidic species, which contributes to acid rain. Now, the soil is capable of neutralizing a certain amount of acid. But as you all know, everything that is too much or anything that is too much is always bad. And the amount produced by the power plants using inexpensive high sulfur coal has exceeded this capability of the soil that we're talking about. Soil is also adversely affected by acid deposition with the consequences such as soil erosion, sedimentation of waterways, and changes in animal habitat. Even limestone and marble structures deteriorate due to acid rain. So it is really obvious it is not just us people who are affected with this acid rain, but also the environment.
Hi, good day everyone. So today we will be discussing about the emissions from automobiles. First is the greatest visible source of air pollution and greenhouse gas emissions is automobiles or the autos. Since the 1970s, pollutant emissions from automobiles and other internal combustion engine powered vehicles and machines have dropped by more than 90%, and as we experience global warming, this is a good news for us. Next. During the same time span, however, the number of automobiles has risen many times, and it results in a considerable increase in pollution and greenhouse gas emissions. So we can say that this is a bad news for us, And yes, next slide, please. Automobiles fueled by internal combustion engines burning gasoline or diesel fuel emit four primary pollutants. These are first, hydrocarbons. These are also called volatile organic compounds. Number two, carbon monoxide. Three, nitrogen oxides. And four, the carbon soot particles, primarily emitted from diesel fuel vehicles. The amount of air utilized to produce a unit mass of fuel has a significant impact on automotive emissions. The air-fuel ratio, as you may recall, is defined as, and here we can see the equation or the equation of the air-fuel ratio. Um, the air-fuel ratio is equal to the unit of mass of air over the unit mass of fuel, hence the term air-fuel ratio. The air used in a combustion process is referred to as the stoichiometric or the theoretical air, and the air-fuel ratio is symbolized by the letters under, AF sub S. Equivalence ratio is the ratio of real air-fuel ratio to stoichiometric air-fuel ratio. We can see here the equation, a small letter phi, or in this case, the equivalence ratio is equal to the real air fuel ratio over the stoichiometric fuel ratio. And, next, the mixture is called lean fuel if it contains more than theoretical air or excess air, and the equivalency ratio is less than 1. I repeat, the mixture is called lean if it contains more than theoretical air and the equivalency ratio is less than 1. Second, the mixture is rich if it contains less than theoretical air and the equivalency ratio is greater than 1. That's why we have the phrase, mahangin ang gasolina dyan, wag tayo magpagas, because that's what it means. Next, automobiles or the autos have environmental consequences that go beyond pollutant and greenhouse gas emissions from the exhaust. For example, disposing of cars with the least amount of environmental damage remains a challenge. Around 75% of automotive materials are recycled and repurposed in the United States. The other 25%, however, or those that cannot be salvaged anymore, are disposed of in a landfill. Other environmental hazards associated with autos include lead emissions from the use of leaded gasoline in some parts of the world. Second is the chlorofluorocarbon emissions from automobile air conditioning. And last, the waste motor oil. Here in the graph, we can see the effect of equivalence ratio on the amount of emissions in a gasoline burning internal combustion engine. We can see here that the nitrogen oxides are at its highest peak whenever the equivalence ratio is approaching to 1. And we can also and we can also see here that there are significant increase in hydrocarbons and carbon oxides when the equivalence ratio is greater than 1 or when the fuel is rich. So here we have a sample problem on how much pollutants will be emitted by an average car. An average car emits 0.79 grams of hydrocarbons, 8.73 grams of carbon oxides, and 0.56 grams of nitrogen oxides per mile. How much hydrocarbons, carbon oxides, and nitrogen oxides will be emitted by an average car during a 10-year period if it is driven 13,000 miles per year? So here we can see the solution. So by multiplying all the given values, the time period multiplied by the annual drive multiplied by the unit of hydrocarbon emission, we get 103 kilograms of hydrocarbons. Next. Same here, we can see that by multiplying all the given values, we get the value of carbon dioxide emissions with 1,135 kilograms, and that's we can say that that's a lot. Next, nitrogen oxides emission is equals to time period multiplied by the annual drive multiplied by the unit nitrogen oxide emission, and we get here 73 kilograms of nitrogen oxides emission. Therefore, an average car is responsible for about 10 kilograms of hydrocarbons, 114 kilograms of carbon oxides, and 7 kilograms of nitrogen oxides emissions to the environment per year. So we can see here the effect that the car has brought in our global warming. Next. So we have here the catalytic converter. So first we will define what the catalytic converter is. Um, a catalytic converter is an exhaust emission control device that converts toxic gases and pollutants in exhaust gas from an internal combustion engine. And it converts it into less toxic pollutants by catalyzing a redox reaction. By converting 90% of toxic emissions into less dangerous gases, the catalytic converter helps to minimize airborne pollutants that can harm people and the environment. A properly maintained catalytic converter increases your car's efficiency, which has a direct impact on its general health and performance. So, not only that, the catalytic converters help in mitigating our global warming problems, but it also helps you increase your car's efficiency because it cleanses um, the internal combustion engine that a car burns for every fuel that it consumes. Next, the converter, which is a chemical chamber, is forced to flow hot exhaust gases from the combustion chamber. In order to promote treatment processes, some catalyst materials are placed in the chamber. Hydrocarbon and carbon oxide that exist in the combustion gases react with O2 in the converter to form H2O and CO2, or the water and the carbon dioxide. Hydrocarbons and carbon oxides that exist in the combustion gases react with O2 or the oxygen in the converter to form that's what's water and carbon dioxide. So we can see here the equation or the conversion that takes place whenever a catalytic converter is used. Next, the constants M and W, A, B, and C are needed to balance the chemical equation in this case. Another reaction is the water-gas shift, which employs water as the oxidant instead of oxygen. Several reactions are possible to convert nitrogen oxides to acceptable components such as the following. And we will not delve into that. So next. At chamber temperatures of 600 to 700 degrees Celsius, the foregoing reactions are easily carried out in the converter. However, because the converter contains catalyst materials, these reactions can occur at temperatures ranging from 250 to 300 degrees Celsius. Catalytic converters are particularly effective in decreasing hazardous emissions, or hazardous emissions rather, since exhaust temperatures in vehicle and other transport engines are typically between 300 and 500 degrees Celsius. Next. When a converter temperature reaches 400 degrees Celsius or above, a well-functioning catalytic converter reduces hydrocarbons, carbon oxides, and nitrogen oxides components by more than 90%. When the temperature drops, the efficiency of the converter decreases. The air-fuel combination should contain some extra air for a converter to adequately treat hydrocarbons and carbon dioxide components. As a result, the converter works best with lean air-fuel ratios. Occasionally, gasoline engines run with high mixes, particularly during startup and acceleration, and the catalytic converter becomes ineffective. When a combination is close to stoichiometric, however, the converter is most successful in nitrogen oxides conversion, and the converter loses its ability to handle nitrogen oxide components in lean mixes. Catalytic converters are also used in diesel engines, however, they should be designed to convert carbon soot particles as well. Larger flow passageways in the converter are used to achieve this. Because diesel engines typically use lean mixes, their converters are ineffective at removing nitrogen oxides. As previously stated, the solution for diesel engines is to use excess gas recycling. Next. On the surface of ceramic passageways, catalyst elements are found. Their job is to speed up chemical reactions in order to remediate contaminants. Aluminum oxide is the most typical material utilized as the converter's ceramic ingredient. Catalyst materials include platinum, rhodium, palladium, and iridium. Platinum reacts well with hydrocarbons, palladium reacts well with carbon oxides, and rhodium reacts well with nitrogen oxides. Next. Some components found in fuels such as lead and sulfur and others found in engine oil additives such as zinc, phosphorus, antimony, calcium, and magnesium can poison catalyst materials and cause catastrophic damage to catalytic converters. Lead should be avoided in particular since it quickly poisons catalyst materials. Leaded gasoline cannot be used in a catalytic converter engine. Lead is a hazardous contaminant that has severe harmful effects on the liver and kidneys. Hence, it has been phased out of gasoline engines since the 1990s. When swallowed, it builds up in the blood, bones, and soft tissues. Um, Leaded gasoline contains about 0.15 grams of lead, which 10 to 50% of it ending up in the engine exhaust. Sulfur is present in diesel fuel, which is transformed to SO2 or the sulfuric oxide during combustion. When SO2 containing combustion gases passes through a catalytic converter, they may mix with O2 to generate SO3, which with the help of catalyst materials. After then, SO3 is changed to H2SO4, which is a component of acid rain. The catalytic converter gets degraded as a result of this process. So here is an example of a catalytic converter with a honeycomb structure. Next. This is the example of a catalytic converter with a packed spheres inside it. And third is as an example or an illustration of a damaged converter showing its inside structure. Next is the greenhouse effect. The greenhouse effect happens when gases in the Earth's atmosphere capture the heat of the sun. The Earth is substantially warmer as a result of this process than it would be if it didn't have an atmosphere. The greenhouse effect is one of the factors that contribute to Earth's pleasant living conditions. So we can say that greenhouse effect in itself is not such a bad thing because without it, we would practically be living on Mars since the temperature there is so low that it is still uninhabitable up to this day. Um, the greenhouse effect allows life to exist on Earth by keeping the planet warm, approximately to 30 degrees warmer. Excessive levels of these gases, on the other hand, disrupt the delicate balance by retaining too much energy, causing the global average temperature to rise and the climate in some areas to alter. Global warming or global climate change are terms used to describe the unfavorable effects of the greenhouse effect. You um you have probably noticed that when you leave your car under direct sunlight or on a sunny day, the interior of the car gets much warmer than the air outside. And you may have wondered why the car acts like a heat trap. This is because glass at thicknesses encountered in practice transmits over 90% of radiation in the visible range and is practically opaque or non-transparent to radiation in the longer wavelength regions. Therefore, glass allows the solar radiation to enter freely but blocks the infrared radiation emitted by interior surfaces. This causes a rise in interior temperature as a result of the thermal energy buildup in the car. This heating effect is known as the greenhouse effect since it is utilized primarily in greenhouse gases. Global climate change is a problem in recent decades due in part to the excessive use of fossil fuels such as coal, petroleum products, and natural gas in electric power generation, transportation, buildings, and manufacturing. As of 2019, the CO2 concentration in the atmosphere is at 410 parts per million. Sorry. As of 2019, that CO2 concentration in the atmosphere is at 410 parts per million, or 0.41%. This is 20% greater than a century ago, and it is expected to rise to almost 700 parts per million by 2100. By purchasing an energy efficient car that uses less fuel over the same distance and driving responsibly, carbon dioxide and other emissions can be greatly decreased. Fuel conservation saves both money and the environment. For example, buying a vehicle that gets 30 miles per gallon rather than 20 miles per gallon would prevent 2 tons of carbon dioxide from being released into the atmosphere each year by while saving $900 per year. Recently, there have been reports that there are scientists around the world that are being arrested for participating in a protest which calls out the use of fossil fuel by giant corporations such as the JPMC or the JP Morgan Chase Bank, which, according to Dr. Peter Carmus, is the worst fossil fuel bank in the world. This, these arrests lead to a controversy that became a trend around the world where people would post infographics about what's happening and uses the hashtag Let the Earth Breathe as part of the protest that scientists in the NASA started. What can we do to help as a normal person? First, we should save electricity. Second is save and don't waste water. Next, plant more trees and plants. Fourth, lessen the use of plastics. Fifth, don't burn plastics, rubber, or anything that can affect the ozone layer. Sixth, reduce, reuse, and recycle. 7. Avoid smoking. 8. Drive less. 9. Delete unwanted emails because apparently unwanted emails carbon emissions that the 500 contribute to carbon emissions, and that the 500 emails that 500 unread emails that we are keeping is equal to a 175 grams of carbon dioxide, and that's a lot. Lastly, we should spread awareness on how we can mitigate this problem. That's it for me. Thank you so much.
Carbon dioxide production. In a fuel containing carbon is burned, carbon is first converted to CO by the reaction C as O2 into CO, and then to carbon dioxide by the reaction CO plus 1 of O2 plus the carbon dioxide. CO is a very undesirable and poisonous emission. Carbon dioxide is not a pollutant. It is undesirable because it is the primary greenhouse gas of concern regarding global warming. All fossil fuels, coal, such as coal, oil, natural gas, contain carbon. Burning more of these fuels corresponds to more carbon dioxide production. The carbon dioxide emissions can be minimized by replacing fossil fuels by renewable energy sources such as solar, wind, biomass, hydro, and geothermal. The consumption of fossil fuels may also be reduced by energy efficiency. Assuming complete combustion with air with no CO in the products and 1 kilomole of HCl is burned, kilomole of CO2 is produced. For example, if octane is burned completely with stoichiometric amount of air, the complete combustion reaction is C8H18 plus 12.5 O2 plus 3.76 N2 equals to 8 CO2 plus 9 H2O plus 12.5 times 3.76 N2. That is when just 1 kilomole of C8H18 is burned. 8 kilomole of CO2 is produced. In general, the amount of carbon dioxide production from the mass of fuel can be determined from this equation. The table gives the amount of CO2 production per unit mass of fuel for common fuel. When 1 kilogram of natural gas, approximated as CH4, is burned, 2.75 kilograms of carbon dioxide is produced. As shown in the table, it appears that the combustion of natural gas can produce amount of carbon dioxide production among fuels. For example, 11% less carbon dioxide is produced per unit mass of fuel when natural gas is burned instead of gasoline. Approximated as octane, C8H18 in car. When coal, oil, and natural gas are burned in a combustion unit to provide thermal energy, as in a space heating system or boiler of a power plant, the amount of carbon dioxide produced by natural gas is about 40% less than that by coal. This is due to much higher energy content of natural gas per unit mass of fuel compared to the coal. Natural gas also emits less nitrous oxide, nitrogen oxide, NPN, and more SO2 compared to coal and gasoline. Thermal and environmental benefits of natural gas compared to coal and oil has made it an attractive fuel for electric power generation and space heating. For these reasons, many consider natural gas as a clean fuel. However, natural gas is still a fossil fuel and its combustion results in considerable amount of carbon dioxide and pollutant emissions. Methane and CO are other notable greenhouse gas emissions as well as air pollutants, even though their emission rates are much lower than carbon dioxide. Average and total emissions of common greenhouse gases, CO2, CH4, nitrogen oxide in the U.S. power plants are given at table. Approximately 743 grams of carbon dioxide are emitted to the environment for each kilowatt hour of electricity produced using fossil fuels. This value is decreased to 516 grams per kilowatt hour when nuclear and renewable power plants are also included. Methane and NTO emissions can also be explained as carbon dioxide equivalent in terms of their effect on global warming. Global warming potential. Defined as the ratio of the global warming effect of a given mass of a substance that caused by the same mass of carbon dioxide. Carbon dioxide is the reference gas used in measuring the GWP and by definition has a global warming potential of 4. Other greenhouse gases include CFCs such as R-11, R-12, and R-113. This also causes stratospheric ozone depletion. Hydrochlorofluorocarbons such as HCFC-22, hydrofluorocarbons, perfluorocarbons, and sulfur hexafluoride. The contribution of other greenhouse gases is much less than carbon dioxide. It is estimated that about 85% of the global warming emissions in the United States is due to carbon dioxide. For example, carbon dioxide production from the combustion of coal. Consider a coal with the following composition on a mass basis: 80% C, 5% H2, 6% O2, 2%, 0.5% S, and 6.5% ash or non-combustibles. This coal is burned with stoichiometric amount of air, as seen in the figure. Neglecting the ash constituent, determine the amount of carbon dioxide produced per unit mass of coal. For the solution, we consider 100 kilograms of coal for simplicity, noting that the mass percentages in this case correspond to the masses of the constituents. The mole numbers of the constituent of the coal are consider 100 kilograms determined to be, as seen on the figure, for C, 6.67 kmol, H2 equals to 2.5 kmol, O2 equals to 0.1875 kmol, N2 is equals to 0.07143 kmol, and NS is equals to 0.01563 kmol. Ash consists of the non-combustible matter in coal, therefore the mass of ash content that enters the combustion chamber is equal to the mass content that leaves. Disregarding this non-reacting component for simplicity, the combustion equation may be written as this equation. The forming mass balances for constituents would substitute the variables for C 6.667, for H2 2.5, for S 0.01516, for O2 0.1875, plus 8 pH, and so forth, or equals to 7.745, and for N2 is equals to 29.19. Substituting the balanced combustion equation without ash becomes this equation. The amount of carbon dioxide production per unit mass of fuel is 3.14 kilogram carbon dioxide per kilogram of fuel. Atmospheric ozone depletion. Ground level ozone is a pollutant, but the ozone or O2 that exists in stratosphere, which is 10 to 40 kilometers above the Earth's surface, is desirable as it protects Earth from harmful ultraviolet radiation of the sun, mostly the most intense radiation known as ultraviolet B or UVB. The UV radiation lies between the wavelengths of 0.01 and 0.43 millimeter in solar spectrum. The UV rays are to be avoided since they destroy protein and DNA molecules in biological tissue. As a result, they can kill microorganisms and cause serious damage to humans and other living beings. About 12% of solar radiation is in the UV range, and it would be devastating if it were to reach the surface of the Earth. Fortunately, the ozone layer in the upper atmosphere acts as a protective blanket and absorbs most of this UV radiation. Discoveries of holes in the ozone layer in the late 1970s and 1980s have prompted the international community to ban the use of ozone-destroying chemicals such as the refrigerant freon and other CFCs in order to save the Earth. Chemical reaction of CFCs in the stratosphere reacting with the ozone can be described by the following reactions. In the first reaction, chlorofluoromethane is photodissociated under the effect of intense radiation. Yielding chlorine atom, the atom easily reacts with ozone to produce chlorine monoxide and oxygen molecule. Thus, breaking the ozone stratosphere also contains atomic oxygen which reacts with ClO to produce Cl and O2 in the final reaction. As a result, free chlorine atoms are responsible for breakdown of ozone. The CFCs have been extensively used as refrigerants in refrigerators, air conditioners, and heat pumps from 1930s to 1990s. The CFCs used in the refrigeration systems eventually end up in the atmosphere through leaking during its use or outlets as provided. Chlorine is also introduced to the atmosphere by salt in the ocean, volcanoes, and industrial processes. The first member of the CFC family of refrigerants was refrigerant 11, developed in 1928 by General Motors Research Laboratory. Of several CFCs developed, the research team settled on R12 as the refrigerant most suitable for commercial use and gave the CFC family the name. Harmful effects of CFCs. Fully halogenated CFCs such as R11, R12, and R115 do the most damage to the ozone layer. The non-fully halogenated refrigerants such as R22 have about 5% of the ozone depleting capability of R12. The ozone crisis has caused a major stir in the refrigeration and air conditioning industry and has triggered a critical look at the refrigerants industry. It was realized in the 1970s that CFCs allow more UV radiation into the atmosphere by destroying the protective ozone layer. As a result, the use of some CFCs is banned in 1987 by Montreal Protocol on such set to deplete the ozone layer, which was signed by 170 countries. Refrigerants that are present in the ozone layer that protects the Earth from harmful rays have been developed. The once popular R12 has largely been replaced by the chlorine-free R124. It is mostly used in household refrigerators and automotive air conditioners. R134A is a hydrochlorocarbon and is the first non-ozone depleting fluorocarbon refrigerant to be commercialized. Nuclear waste. Nuclear waste is a hazardous waste that contains radioactive material. A single nuclear power plant using fusion reaction in the reactors typically produces thousands of megawatts of electricity. 1 kilogram of fission nuclear material can release 1,011 kilojoules of thermal energy, which is roughly 2 million times the energy released when 1 kilogram of fossil fuel burns. Note, however, that only about 4% of the nuclear fuel is fissile uranium-235, means a unit mass of fissile nuclear fuel can provide about 80,000 times more energy than the unit mass of fossil fuel. Some people may regard nuclear power plants as a potential solution to air pollution and greenhouse gas emission. This is because the air pollutants produced by the combustion of fossil fuels such as AC, carbon soot particles, CO, sulfur oxides, and hydrogen oxide are not generated after a nuclear fission reaction. In addition, a nuclear reaction does not generate any carbon dioxide. It's the major greenhouse gas. Other people, however, do not consider nuclear energy as an alternative future fossil fuels due to safety of nuclear power plants and concern over safe and permanent disposal of nuclear waste. Harmful effects of nuclear waste. The Chernobyl accident that occurred in 1986 at the Chernobyl nuclear power plant in Ukraine in former Soviet Union was the worst nuclear power plant accident in history. 31 people died during the accident, and it affected much of Western Soviet Union and Europe in long-term effects. The most recent nuclear disaster occurred in Fukushima in Japan. At, at the Fukushima 1 nuclear power plant in 2011. The accident was initiated by the devastating tsunami of and an earthquake. When a used nuclear fuel is first discharged, intense levels of radioactivity exist. The content of the fuel changes as time passes. However, the total radioactivity does not decrease significantly. After 100 years, percent of total radioactivity can be as high as 99%. Therefore, once a nuclear fuel goes through a fission reaction, it will be radioactive for thousands of years. There are also low-level waste produced in nuclear power plants. They include gloves, towels, lab coats, filters, and other materials that may contain small amounts of radioactive material. These wastes are carefully handled by placing in drums and stored at some burial grounds. Radioactive emissions are harmful to living organisms. The higher the level of radioactivity, the higher the potential health effects on humans. Long-wave radiation with biological material causes cell damage. Increased rate of cancer with exposure to nuclear radiation relates to death.
For the additional information, there's a lot of news circulating online that scientists all over the world, more than 1,200 scientists in 26 countries to be exact, were tested on Wednesday, April 6, after a release of new climate report by the United Nations. They are demanding for our climate actions since the situation that we are in now is so much worse than the previous climate report. And officials are arresting them for scientist rebellion. This is really getting out of hand and should be addressed thoroughly and urgently. Scientists like Kalmus, the one who protested, one of the scientists who protested, are hoping their effort to shed light on what's happening and how urgent the situation is. They are hoping that it will inspire corporations and governments to begin cutting down greenhouse gas emissions quicker. But sadly, by looking at the poor amount of coverage this latest protest received in the media, it is clear they'll need a helping hand from the rest of the public, and that is us. This is a reminder for all of us that what we are facing right now is a serious matter and should not be taken lightly. Scientists are doing their best to warn all of us, yet none of us are taking this matter seriously. And that concludes our presentation. We hope that you learned a lot of things regarding energy and the environment. Thank you.